We'll start with water and not So of course, the biggest one of those languages is Russian. We do not understand Russian, but we can read it. So yeah, that comes from Macedonia. And then about the Netherlands, I moved in the Netherlands almost 3 years ago, and my entire group almost is foreigners. So when I asked them what were the things when they came to the Netherlands that surprised them or they found very interesting, I was expecting to hear the bike. So this is really how a bike parking at a train station looks like. Or cheese. So Dutch people eat a lot of cheese. The tulips and the windmills. I think this is the most famous postcard out of the Netherlands. But none of those things were what my students were impressed with. Everyone said, Dutch people are so tall. So this guy over there is literally a student at the student event, and this is a professor from our group. So yes, Dutch students are very tall. Statistically speaking, Dutch men are second in the world, and Dutch women are first in the world. That doesn't really mean that everyone is that tall. But then another funny thing that all my students complain about, and I would also include myself in the group as well, is that Dutch people all they eat. We have another confirmation here. So this is how a Dutch sandwich looks like, and literally all Dutch people eat this for breakfast and lunch. And they call it a sandwich, but I don't know if that's a fair way to all the rest of the sandwiches in the world, because it's literally two big pieces of bread and a very thin slice of cheese. So yeah. Another very interesting thing. So I arrived here on Sunday, and I was in Campinas, and now I'm here. And one of the things that I keep mentioning, and probably being very, very annoying to my student by now, is that a lot of the buildings look alike. So I think these buildings can probably be from around here, but they're actually from Skopje. For example, this is the main university building where I used to work. This is the Faculty of Mechanical Engineering. This is my high school where I went in Skopje. And this is literally a picture from, I don't know, Skopje in the 60s or something, where how it used to look. And I think this is the time where these buildings were actually built as well. So I don't know why it looks very similar, but maybe we should discover more. So I found it very, very interesting. Now a bit more on the serious stuff. So Renato already said in the introduction, my main idea in the research is to design of large-scale adaptive metastructures, mechanisms, and machines that are able to change properties in time to better fulfill their tasks. And maybe just to define adaptation in this context is the ability to recognize changes occurring in the environment and then adjust internally to respond in a desired way. So if we start with why we need adaptation, I think nowadays we're kind of all facing, regardless of the research context that we're working on, that everything becomes connected with all the technology in the sensing, all the machines want to be better connected. And I think we're kind of creating ecosystems for situational intelligence, where everything that we design needs to have a certain level of responsiveness towards the environment. But how I approach this problem is through structures and mechanisms, and we develop certain concepts that rely mainly on large deformation. So we deal a lot with flexibility and compliant mechanisms. We mainly use smart materials for actuation. We are trying to see the limits of size. So usually in smart materials and in compliant mechanisms, the trend in the last couple of decades has been towards making things smaller and smaller and smaller so that they would fit in, for example, chips or biomedical devices. However, there has not much been explored if we need to, when we try to go on the larger scale. However, we have detected that certain concepts can really benefit of this type of adaptation. And then another approach that we are trying to explore is if we can use the environmental conditions and changes in the weather or in the environment for self-actuation using smart materials. So the reason why we approach this and we think that this is possible, I mean, if you start looking at bio-inspired designs, or actually if we start looking at nature, then we do see compliance or flexibility at quite a large scale. So we do see, elephant trunk or whales or different animals that have very, very high level of flexibility. While if we look on the engineering side, we're still very limited in size. There are very variety of smart materials that material scientists have developed in the last couple of decades, and the technology is still going more and more in developing unique featured materials. However, a lot of these materials are very much still in lab settings. So commercial value is not there yet. And maybe one of the things to bring smart materials to a commercial side, it would be if we can actually harness the energy that is happening in the environment in a way to self-actuate them. So smart materials can go, for example, this is just for temperature responsive, so from -40 to 300. And then we see if we know where we want to have an application and what would be the temperature range, maybe we can design things that can utilize the changes in the temperature versus usually designing things that need to withstand that and deal with it. So in terms of applications and concepts, we are trying to see whether grabs or handling equipment in ports can benefit out of these concepts in adaptivity. We are looking into different designs of compliant mechanisms and bio-inspired things. And I live in The Hague, which is on the coast of the Netherlands. And this gift here is literally a scenery that I have seen. So there's this artist, he's called Theo Jansen, and he builds he calls them strandbeest or beasts of the beach. And he builds them out of plastic rods. That's all it is. So he found a way to make these structures, and they're literally powered by the wind. So the Netherlands is really windy, and they're very impressive. They're huge, and when you see them, quote unquote, running around, it is impressive. So if an artist could figure out a way to, use wind for locomotion of these beasts, then maybe us as engineers can be inspired for this type of concepts. So I have clustered my project that I'm just going to introduce very briefly today in the talk on the adaptive structure. So we do quite a lot in metamaterials design, especially using smart materials in the unit cell characterization. A bit on the compliant mechanism side, so also for metamaterials, but using very compliant unit cells, and using smart particles for design of soft robots. So I will start with the design for additive manufacturing of nickel titanium lattice structures with tailor mechanical properties. So this project deals a lot with characterizing nickel titanium, which is a smart material that has two features. One is the shape memory effect, which means that you can load a structure made out of shape memory. A spring is the usual typical example, so you can extend it. It will stay in the deformed shape after you remove the load, and then if you heat it up over a certain temperature, it will recover its original shape. And then another feature is the super elastic response. So it's a metal, but it can exploit up to 8% of recoverable strain, which compared to other metals means that it can be used for energy absorption or impact loading, and use these recoverable strains in certain way. So a lot has been done in exploring 3D printing of nitinol and understanding the process. And now we want to take it to the next step where we want to understand what's happening when we actually 3D print lattices from nickel titanium. So we want to, eventually the goal of the project is to functionally grade at the material level. So have different compositions of nickel and titanium in the process, but also on the unit cell level that we can functionally grade and change the size, the orientation, and the shape of the unit cell. So why this happens and why it would be good for energy absorption is the phase transformation, the mechanical transformation of nickel titanium actually has a very big hysteresis that can be used for energy absorption. So if we have these very big, very compliant structures, they can deform in a certain way, then the load is removed and they can recover the shape. So my student took existing metamaterials or the very conventional and traditional shapes, and then he explored how he can manufacture them. So we characterize the nickel titanium thermomechanical properties, and as expected, we did receive this hysteretic behavior that we can then use for characterization of the metamaterial itself. So we have octet and BCC structures. So these are the representative unit cells. And then we tried the characterization from the experiments to put it in the model and understand better what's happening in the behavior of the structures. So what my student noticed is that we have temperature dependent behavior, which in a way it was expected, but it hasn't been really characterized. So he went on and discovered these anisotopic temperature dependent transformation stresses. So if we want to actually really precisely design something, then we also need to know the temperature range where this structure will operate so that we can better capture the behavior and benefit out of it. So the structures that we printed look like this. So this is the octet and BCC. And then we also explored the grain formation and how that affects the properties overall. And what we discovered is that tailorability of the loss factor can be done by changing the shapes and sizes of unit cells. These hinges play the biggest role in the energy absorption in terms of the transformation of stresses. So in future iterations, that's where we'll focus on in understanding how to better design these hinges. And one of the things that we discovered during, let's say, these initial experiments is that even though we expected high recoverable deformation, you see that fracture happens. So there is a need of understanding better what's happening with the processing parameters so that we can actually really benefit out of the properties of this material. I will go next towards compliant mechanisms, and I think this fits nicely because basically what we are trying to do with this nickel titanium is have unit cells that have very large compliance, so something like this, where the deformations are high, because if we want to recover and absorb a lot of energy, then we really need to go for large deformations. So these are contact-aided compliant mechanisms, and this is a collaboration with Penn State University in the United States. So in order to design this type of largely deformable unit cells, if we use commercial finite element method, that's computationally extremely expensive, especially if we want to add on, for example, nonlinear material like nickel titanium. So in order to be able to optimize them, we looked into simpler approaches for modeling. So one of the approaches that we have developed is pseudo-rigid body modeling, and this is a known Wayne compliant mechanism for simple model, and we have managed to actually incorporate a nonlinear material component into this pseudo-rigid body model so we can capture the behavior of the mechanisms from the material and also from the nonlinear geometry side. We've also developed beam models that can capture the superelasticity of nickel titanium, and now the next stage would be to actually compile certain metamaterials that would really have these large deformations. The approach that we actually want to take is to go towards building block approach. So understand these beams and how their behavior is, and then try to compile different configurations of these beams so that we can get complex shapes. So the initial shape that we're working with right now is these arcs or S-curves or these V shapes. And we're looking into the properties of the material, but also the manufacturing opportunities that there exist. So what we have discovered, for example, if we compare different designs of these V and S shapes, we can really have very tailorable behavior of the structure. So it depends on the application. We can really see what kind of energy absorption we want and tailor it specifically. The next project would be also on smart materials, but different kind of smart materials in printing, which is piezo truss lattices. So piezo is a material that has electromechanical coupling where stresses and strains are directly connected with electrical energy, voltage and current. So in natural piezoelectric materials, we have certain modes that are non-zero components, or that do the transformation from mechanical to electrical energy and vice versa. But this can be a limiting factor if we want to do energy harvesting, for example. So then we apply machine learning to actually design lattices that can have tailorable properties in all directions. So by orienting these trusses, then we can activate modes on a structure level that on a material level would not be possible. So the approach that we have is we have these 7 basic lattices, and then they are loaded in different configurations. They're put together, so we have 262 unique topologies, and then from them we go along further and we can actually generate inverse design. So by plugging in what kind of properties we want in these piezo truss lattices, we can actually get the shape of the unit cell that the goal is then to figure out a way to produce it. And we are working with colleagues at Aerospace Engineering that have developed a manufacturing technique for embedding barium titanate particles into a resin and then 3D print. So this is where we are with this project at this stage, and we have some promising results. So we're hoping that this technology really will support the 3D printing of piezo, because we are using a commercial printer. So we only embed particles into the resin instead of using highly sophisticated 3D printer. The next project will be Ana's project. So Ana is from here, from Brazil, and she was my first PhD student at TU Delft. Ana has super cool project that is for metamaterials for underwater noise mitigation. So one of the things that is a very big topic and trend in Europe, and especially in the Netherlands, is energy transition. So the EU has very strong measures in place to help with the energy transition. So you can imagine that Netherlands being close to water, offshore wind has taken a very big way. And another thing that is very specific, the water, the North Sea, so the water between the UK and the Netherlands is very shallow. So that makes the a way to install the turbines in water very suitable for monopiles as foundations. So what that means is that these wind turbines actually have a very big monopile that is embedded into the seabed, and then the turbine is mounted on top of it. But to place these monopiles into the seabed, they're hammered, which means that they have these big hammers. And I think Anna found this figure when we're talking about size. You can see this is a car and a truck, and this is the size of these hammers. So these hammers hammer the monopiles into the seabed, and these monopiles are 6, 8, 12 meters wide and 60, 80 meters long. So the noise that is coming from this piling is very harmful to the marine life. And there have been concepts that are reducing. So these are called bubble curtains. So air is put into the water and while the hammering is happening. But the intention of putting more and more windmills in the North Sea is not only that the size or the number is getting bigger, their sizes are getting bigger. And with their sizes getting bigger, then the frequencies are getting lower. So these bubble curtains don't work anymore. So what Anna is actually proposing, and we have shown that there is benefit from a concept, is that when the hammering is happening, if we design a metastructure that is on top of the monopile and below the hammer, then we can configure a unit cell that can be tailored to the specific harmful frequencies for the marine life, and we can filter out the energy that's harmful while keeping the energy that's necessary for pile driving. So we have measures in terms of, let's say, legal levels of this noise. So that is what has to be enforced so that the construction can continue. And this threshold is known. So for us, that is a very important parameter, together with the monopile size, that we can actually design this meta interface so that it can really filter out the energy that is harmful while keeping the energy for the pile to be driven into the water. And to do that with, let's say, these input parameters, we want to do inverse design so that for any type of monopile, we can actually propose a design for this meta interface and then take it and then manufacture it and be in place. So we have filed for a patent. The patent has been approved. We're also working with a company to help us set up the experiment. So we are very excited to see if the numerical analysis and concept we proposed is going to turn out as we expect. The next project is the project on actively stimulated particles as unit cells. So this is a bit of a stretch of the metamaterial idea. However, there has been this trend of going from structured metamaterials versus towards unstructured, which means that the unit cells do not really connect to each other, but they are independent from each other and they're just within an enclosed volume. So kind of combining that idea with the idea of granular jamming in soft robotics. And granular jamming as a concept is, I think, something that at least as kids we've all tried it. If you have a bag of sand and if you put it around something, if you vacuum the air out, then it will create forces around the object and you can lift it up. But then you always depend on a vacuum pump to take the air out. But what creates this feature basically is the change of packing state of particles. So when you go, let's say, from one state to the other and you vacuum the air out, you change the packing state of the particles. But another way to do it is if you have the particles in a confined volume, if you can find a way to change the volume of the particles, so for example, they expand, then you can actually, again, change the packing state of the particles. Or if you have particles from different shapes, if you have a membrane that can shrink, again, you can change the packing state of the particles. So we are exploring this as a concept for soft robotics, but especially we are interested in larger scale. I will use the example again from offshore wind. For example, blades, they are still handled, which means picked up from one place to the other in a very conventional way. So with cranes and ropes, and this is a very labor and time consuming operation. And since a lot of blades and a lot of equipment like this needs to be handled, then maybe bringing concepts from soft robotics that have proven to be good for handling randomly shaped objects on the smaller scale into this larger scale might be a good idea. So how we have started exploring this is have, let's say, two modes of doing it. So one way is we have same particles in two chambers, and then particles from one side expand their volume. By creating this expansion in one of the chambers, then we can achieve bending on one side. Or if we have particles with different volumes, then by shrinking the membrane in a way, we can achieve the same concept. And the idea is that maybe we can engineer these particles and make them out of smart materials, for example, with 4D printing, and then have particles that have different shape. And maybe we can stimulate them with temperature change or humidity change or electricity or magnet so that their packing state changes. And some of our initial models are based in Abacus, so commercial FEA, where there is coupling with discrete element method. So that showed to be a nice way to capture this behavior. So what we realized is whether we use a complete FEA model or we use the coupling between discrete element method or FEA, we still get the same behavior. But the coupling is computationally a lot cheaper, so that's the way that we would like to go. One interesting thing that we have discovered with these initial numerical studies is that there is a sweet spot where we can get the best performance between the particle number, particle size, and the membrane, which I think makes it a great problem for optimization at a later stage. Another thing that we observed is that the longer we get, or the number of particles increases, we start getting curling. So it's not only bending, but we start getting curling. And with curling as a concept, this is really nice because if we want to pick up something, then we can wrap around an object and then bring it up or move it in the way we want. So we do want to explore and further exploit this too. So these are the projects that have been ongoing and we have some initial results. Though I have a couple other projects that are at their initial start. So I'll just briefly mention them. I have a project where we would like to see how to design these actively stimulated particles. But in order to understand what is the most efficient way to design them, we would like to see how nature is doing that. So I have a project where we will look into octopus denticles. And one of the cool features that they have is they use dynamic stiffening, which means that if they want to reach something, they can really find their way in terms of reaching. But once they do the interaction with an object, depending on the size and the weight of the object, to come back, what they do is they stiffen in 2 points, which basically they make an arm, they make 2 elbows, and that is the most efficient way to come back. So maybe there is something why nature does it like that. So that's what we would like to understand better and then use the same concept of bringing the efficiency towards the fetching part. Then another project, so TU Delft and the Netherlands is host of the biggest port in Europe, still second biggest in the world, which is the port of Rotterdam. And that creates, I would say, a big drive for research in our university as well. So there is a big push towards making the port greener, and Netherlands has been faced with a lot of pressure to impose restrictions towards the port because that is one of the biggest polluters in the Netherlands. So there. A couple years ago, we applied and we got a big fund from the European Union. It's a 25 million project to explore how the port can actually become greener. And my small fraction in this project is to understand. So one of the pollutants in the port is the movement of containers between different terminals in the port, because this creates a lot of traffic jam. There is sometimes trucks, usually it's done by trucks, so then you have a lot of trucks moving around and then they have to wait. So to avoid this, another way to do it instead of doing it by land is maybe doing it by water, because then the distances are shorter. And there has been a lot of research done on the barge side, so on the vessel side, to make them autonomous and greener, and all of that. And there is also a lot of research on the land side to make the autonomously guided vehicles from one place to the other that take the containers also greener. But to make the system complete, there is not a piece of equipment that's tailored to pick up the containers from the barges and put them on the trucks. So I have a student who is looking into this, and the main problem there is a challenge that has been solved in different industries, but on a smaller scale. So the barges move. So when they are on the water, there is certain instability. So for a piece of equipment to pick it up from a barge that moves, that there is an issue here. So we have to solve the problem of how we can have this piece of equipment adapting to a moving barge, so we can pick up the container and place it on a truck on the land. And then another project that is going to start next year on fluid structure interaction. Again, I would say driven from the industry needs in the Netherlands. One of the things with the offshore wind, I'll bring it up again, is the entire logistics. And logistics in terms of, well, how are we going to make all the parts necessary on land? And then how are we going to install these turbines in the water? And there is massive logistics input, and a lot of Dutch companies are concerned with this, and they're actually leaders in the world in terms of offshore. And one of the problems that has been shown that can really have impact is how these structures, for example, these monopiles that are huge, as we said, 10 meters wide and 60, 80 meters tall, you need to transport them from land to an offshore location somewhere on the water. And you need to do this fast. And the vessels that are used right now, well, they are influenced by the structures, and their dynamics is influenced by the structures. But it hasn't really been explored much what kind of influence this is, where is it coming from, and how dangerous it can be. So if you want to make this movement faster of the vessels from land to an offshore location or between offshore location, then understanding the influence of these big structures on the vessels while they're being transported can really have a big impact. And also right now, for example, they're doing it in few monopiles, so in one row. And they are afraid to put more rows on top of each other because they're not sure of the influence and how that might happen. And we're talking, if we understand this better, then maybe the vessels can be a lot more efficient, a lot more equipment can be transferred from one place to another, which reduces a lot of costs. I mean, here we're dealing with tens of thousands of euros of cost per day of use of equipment. So I'm looking forward to start this project, and let's see how it goes. So I'll start wrapping up. In short, we are looking the scaling up effect in terms of size. So what are the limitations, whether they come from manufacturing or structural integrity that impose, so we can build structures that are compliant or structures inspired from the metamaterial concept. And we try to develop models to capture this. Then we look into inverse design of this type of structures, because we would like to start from the functionality, so the application, know the functionality, and then go back and have a design that will be ready. But in order to do so, we need to understand the additive manufacturing, the process, material, the stimuli, and the mechanical property relationship very good, so that we can put it in the design process. We are working quite a lot with building block segmented approach. So we try to have very well understood mechanically intelligent structures and then put them in different configurations. And we also explore shape optimization and machine learning for inverse design. Another thing that is interesting to explore is, well, how this adaptivity plays a role in machines where the operational conditions are varying, and that is in offshore for sure, because we cannot control the weather and the storms and the waves. That's very changeable. But sometimes also in ports or even in closed environments, the differences can be very large. So we're trying to understand how we can design equipment that can harness or better behave while these operational conditions are uncertain. So we continuously are answering the question of how to design these adaptive structures, mechanisms, and machines. And we are going towards understanding the functionality and then combine smart materials or conventional materials together with the geometry to actually fulfill this. At the end, I would like to thank the most, of course, my students, my group. This is my group. Anna is present here, so they're the ones who are doing all the hard work. Of course, the funding support, and I do want to say I'm very happy to be here. I personally find international collaboration very important and stimulating. I have collaborators in the US, in Europe, and I'm happy to be here and use this as a nice way to show my work and hopefully spark some ideas for collaboration. So thank you very much.
Thank you, Jovana, for the very nice and very fun presentation.
Thank you.
It's nice to have you here. Very nice.
Thank you.
We have time for questions. Does anyone have a question?
How many questions per person?
Let's start with one.
Okay, okay, make one question in two parts then. It's just more like my physical understanding when you tune, you know, the hammer problem that I was working with for a certain frequency in order to, you know, eliminate propagation of the frequency. But then you have the hammering comes with all the spectrum frequencies, right? So how do you tune that for this case when they have like transit load that carries all frequencies?
Anna, you want to answer this or you want me to answer it? I would say go ahead. This is what you deal with daily. Yeah.
So as I understand correctly, so we have this frequency range, right? Mm-hmm. So first we have to identify the critical frequency, that is the frequency lower, higher than the threshold. So we measure the sun pressure level model to the common interface, so I don't have any event cells. So I apply this Hamming impact and evaluate the frequency, the frequency range, and we identify the highest one. And with that, we relate it with the ID modes of the modifiers. So based on that, because we did make this relation between the ID modes and the high sun level model, we just designed the unit cell based on the frequency of the modifier.
For a dominant frequency?
Yes, yes. The dominant frequency, yes.
But maybe if I can add, so her initial study showed that the majority of the noise that's harmful comes from this mode. So if we actually detect this mode and we see what's happening with this mode, and if we attack that one, that should be okay for the most cases. And if we have another mode that might show up, then we can basically design a bit of a different unit cell and go for that mode too. And that, of course, is in ideal conditions if during the hammering, this doesn't change. But one of the things that we are aware that it can be an issue is that, you know, while we hammer, then the monopile dynamic response changes because part of it will be into the soil and part of it is in the water. For right now, just assume that.
Okay, so right now you're studying the piles separately from the water and the soil.
No, it is together, but we don't take in consideration when it starts going down. So we don't take the reduction of length.
Actually, because the critical point is this initial step. It's when the pile is really in contact with the soil. Because if the pile goes, we have some penetration in the soil, most part of the energy goes to the soil, not to the water. And our concern is when the pile is more in contact with water.
Okay.
Well, I think that was the question, right? In that direction.
Yeah, I understand.
Yeah.
This is the problem with like interesting problems that you have more questions as
of course.
It's okay.
I think every time we have a meeting with the industry, we are coming back with more questions and challenges of how to solve this. Because I mean, there are so many things that influence it, and you know, you have to start from somewhere, so you cannot take everything in consideration from the very beginning. And your second part of the question?
Okay, she's letting me ask. What's the difference between bending and curling? Isn't curling just like a stronger bending? In terms of modeling, like what's the line where you have to deal with one or two.
So in the compliant mechanisms community, there is a difference or how people attach themselves, whether it's bending or curling. We don't see it as a difference. However, for us, what is important is if you want to grab something, let's say if you want to design an arm, and then you need to decide, are you going to go with 2, 3, 5 fingers, depends on the application. And then if you go with bending, then you have certain way of how you can pick up things. But then if you want to exploit the curling, then you don't need maybe an arm configuration. Then you can have 2 separate arms like this and then curl around something. So for us, it's interesting in terms of like what kind of object we have and how we can handle it.
So the modeling is the same for both
Yes.
non-linear, everything is
Yeah.
just an imaginary line in terms of application.
Yes. For us, that's what's important. But and as I said, in different community, this is a big thing. But for us, it's just of how the mode of actuation happens and how we can wrap around an object. Thank you.
I have one question, quick question. I see you used shape optimization. And have you ever thought about topology optimization, and how did you come up with the first design?
Again, should I answer or?
Yeah, so the first design, actually, because I go with the single phase unit cells, and usually the basic model is just a mass of pins connected to the external frame. So I thought, why would I don't increase the beam length? So my first idea was this unit cell. And about the shape optimization, I also thought about topology optimization, but the shape was, for me, I think it's a better approach because I have already this basic idea of a resonator, so I have those beams and the mass, and I just want to see if I change the boundary of those structures, how this affects the bending. So the topology, I have to be sure that I have the connections between the frame and the mass of the resonator, and with the shape node, I just analyze the boundaries. But it can be up to choice.
I see. Makes sense.
May I also a background of the story is, so these unit cells we're talking about something that's like 0.5 meter. So we're talking about huge unit cells. And then in order to manufacture this, even though usually for metamaterials, like 3D printing is kind of like the way, we can print everything. But if we actually want to build very big structures, then machining makes a lot more sense. Especially like, for example, now what we're going to manufacture and test is going to be aluminum. So that was the reason why we really wanted to be from one material, so we can actually make it on a larger scale and explore what's going to happen later. So the first idea of the unit cell, it's only Anna, so she deserves the credit for it. Yes, please.
Yeah, nice presentation. So
Thank you.
I'm interested in your Isotopic design. And when you manufacture, after you manufacture, you need to pull, right?
Yeah.
So how do you do? I mean, you pull each truss or the entire chunk of material? How do you do the pulling?
That's a very, very good question. So in this first phase, we are going to pull the entire thing together. So we'll put it between 2 plates and we pull it vertically. However, another idea that we would like to try later is to pull it while it's being printed. So in that case, we can basically pull every strut individually. But in the first go, it's going to be the whole structure altogether.
Okay, so which scale you are talking about the chunk?
So right now we are printing it like, let's say 2 centimeters by 2 centimeters.
Okay.
So that's that's the size that we're working with right now, just to characterize the manufacturing process.
Okay. Have you thought about using the colloquium there in the design?
We have, of course we have, but the collaborator that I work with is a machine learning expert. And then his approach or his suggestion why to go with this one was that we developed our own model for the piezo trusses. So it's very computationally cheap. So we can generate a lot of different designs in a short amount of time. So then that makes it useful that if we have this database, we can use machine learning to inverse design. Thank you.
Any other question? I have another question. In your FSI vessel dynamics program, Do you plan to use any operational research tool like optimization, branching out, or machine learning maybe? Because this seems to be a very challenging packing problem, right? Because you want to pack all the stuff into the vessel and avoid resonance or.
Well, I think that part of the problem would be a later stage. I think initially we would actually really like to understand what's happening if when you have these monopiles, what kind of connection do you need to have with the vessel? How many of these connections? Is there a danger of the behavior of the vessel with the number of monopiles that need to be in place? So I think this is going to be the initial
simulation.
Yes. That would be it. However, we haven't really decided how are we going to go with this simulation. That's still open for interpretation, or let's see how it is. We do have a bit of a preference to start with simple analytical models, and the reason is because if we go with, let's say, full coupling of fluid and structure, this is just way too computationally expensive, especially if you want to model it on a full scale of a vessel and multiple monopiles. So that's what we're thinking right now, but I'm happy to get some advice of what do you think it would be feasible, but we can talk about this later.
Okay, cool. Thanks.
Thank you.
Another question? Oh, we have another one.
Very nice presentation.
Thank you.
About the lattice structures research. The manufacturing process affects the final properties of the structures?
Yes, it does. I mean, that's what we expected that, but even now, once we printed stuff, when we are measuring and characterizing, we see that it influences it a lot. For example, in the nickel titanium lattice structure, we printed different batches of structures to test, and with everyone, we also printed bulk material so that we can see what's happening if we print, let's say, a full structure and a structure with certain geometry. And then we realized that the properties differ. So there are stuff in the processing that is happening, and we are trying to understand that better. So I collaborate with a material scientist that's her expertise, and we're really trying to understand better why certain properties are happening and how we can know what kind of shape to use so that the expected properties are there. Like, for example, we have problem with evaporation of nickel in the process. So yeah, what we expect to have in the structure is not there in terms of composition. Yeah, thank you.
Question?
Thanks for the presentation.
Thank you.
I believe it's a simple question. And how you determine the length of unit cells of your problems, and if it's a maximum size limit to scale to microstructures?
So maybe on the how do we determine? So, for example, in this case, we know what is the energy that we need to decrease to fulfill the task, and we use that and see how many layers of the metamaterial we need to put so that we actually take away this energy from the system. So in this case, that is the reasoning. And I would say it kind of goes case by case. We don't really have a systematic way of deciding how many layers are we going to have from a unit cell. I hope that answers your question.
Yes.
Okay.
One question. At Unicamp, you mentioned you are interested in natural frequency constraints. What, between these projects, which project do you see it as the most important to have a natural frequency constraint? Maybe this one?
I mean, this is the one that I think it would be very interesting because technically or ideally, we can find the frequency and we can put a band gap there, but we don't really have a constraint, or we don't have so much control of how big is this band gap. And when we talk about real application, we cannot be as precise. I mean, things can go a bit out of it. So if we can have these natural frequency constraints, then maybe we can have a bigger region with band gap that we can kind of deliver performance with higher level of certainty.
Okay, cool. Question? Another question? Nothing to do. If not, I thank you very much again. We are very glad with your presence here. Thank you for the nice presentation, and we keep in touch here.
Thank you very much. Thank you for having me.
We will see in our colloquium from today. Thank you, guys.
Thank you. Bye.